Hello, and welcome to another brief video lesson on photometry, differential photometry. Differential photometry is in essence comparing the difference between a target star and a comparison star. This is most useful in time series photometric observations. The direct comparison of a target and a comparison star in the same field of view eliminates other observational variables, leaving a direct differential comparison. For example, light pollution, because light pollution would equally affect the entire frame of the image. It's important to note this process does not derive an absolute magnitude measure, but instead provides differential or relative magnitude changes between the comp star and the target. To accomplish this, we use a process called aperture photometry. Note, if you have not viewed this lesson, pause and review the aperture photometry lesson before proceeding here. Key elements are going to be understanding aperture photometry, what a comparison star is, some stellar magnitudes, and image calibration. The process. Differential photometry uses aperture photometry to compare two types of stars, the target and the comparison. The comparison then reveals a relative pattern of flux of each stars. So what we have on the right is we have a star chart from the AAVSO. In the center here, you see a plus designation. And from the AAVSO, that is the target star, in this case, AM Her, which is AM Hercules, this variable star in question. Now, there are other stars in here that have numbers by them. There's a 132, 141, 15.3. What these are known comparison stars and their steady state magnitudes. So in this case here, where it says 132, that means 13.2 is the magnitude of that. Take this star over here, 118 is really 11.8 is its magnitude. So these are comparison stars that can be used of a known magnitude against the primary. Now note, we don't always have to know the magnitude for a comparison star to be useful. What we do have to have for a comparison star to be useful is it must not change in its brightness over the course of the image set. So if we're taking a 3-hour time series, multiple images of an exoplanet transit, let's say, the comparison star must be of a stable magnitude that entire time. It does not have to be known, but it has to be stable. So to produce differential magnitude, we have the following steps. We have to determine the instrumental magnitude of the variable star and the comparison stars. And an instrumental magnitude is simply a brightness that you see on the CCD chip. We average these magnitudes of the comparison stars for that image. Then subtract the average comparison star of instrumental magnitude determined in step 2 from the variable star's measured or instrumental magnitude. So we're combining the comparisons and then subtracting it from the variable. What's left over is the differential. Guidelines for the best results in differential photometry. Ensure that each image is already corrected or reduced before you measure it. The AIJ program allows you to image calibrate. That's darks, flats, bias. If your images are processed in the OSS pipeline, they are already calibrated. If not, you can calibrate your own images, and we have lessons on those. You have to select the correct aperture for both the target and the comparison stars so you don't get other stars in there biasing your results. You have to use multiple comparison stars with brightnesses that are similar to the target. Don't have to be known, but have to be similar and have to be steady state. Comparison stars should not be variable. All stars, comparison and target, should be in the same field of view. That's the best practice for differential. Once it's performed via software, you can achieve a table of measurements from these results. You will get a timestamp for when the measurement was received. That is from the FITS header. You'll see the change in the flux of the target relative to the comparison stars and what the associated errors are. Here are a series of comparison stars, and notice how stable they are. Here are 2 dips of a target star showing an exoplanet transit. What you also see on this top exoplanet transit is you'll see a point, a measurement, but then you'll see bars on top and on bottom that look like this. Those are error bars. so you see the error bars produced in that particular transit. In sum, differential photometry is the comparison of a non-variable comparison star against the target star that is suspected to be variable. The advantage of this process are errors introduced by variabilities such as the atmosphere are minimized as it affects all stars in the image in the same way. Appreciate your attention and look forward to seeing you on a future brief video lesson.